This episode is brought to you by Brilliant. It becomes ever clearer that humanity's future is among the stars, a journey to trillions of new worlds. But every journey has to start somewhere, and to reach the heavens, we must first sail from starports here on Earth. A little over a century ago in 1909, Wilbur Wright established College Park Airport in Maryland, the oldest continuously operating airfield. The first commercial airliner arrived in 1914, and the first airport with scheduled international commercial services opened in London in 1919. It was only 16 years from that first 1903 Wright brothers flight to regular international commercial passenger traffic, permitting people to travel almost anywhere in the world in a mere day or two, something we now take for granted. The first manned launch to orbit was 60 years ago, and we're only now starting to see a real stage-up commercial manned spaceflight. There are quite a few launch pads, but there's no place right now where you can go, buy a ticket, get a seat, and fly to space. That time is coming though, and today we'll be asking what those will be like, these ground-side facilities that will take us up to the heavens. And that will be one point we'll be looking at today. Will they be groundside? Or will they be out on the sea on ships or small islands, or even up in the air? For a discussion of those facilities up in space, see our episode The Next Space Station from a few months back, or Spaceports for a few years back. Which does raise a question as to what a spaceport is. Is it a space station in space, or is it a facility not in space for traveling to space or from space? And that's not something we can define just yet, so for today we'll say that any facility on land, sea, or air, meant principally for getting up into space, is a spaceport. So an airport with a sideline launching spaceships is still an airport, even if it has a spaceport terminal in it, I suppose. So they might be on the ground, or in the sea, or in the air, but the nature of the launch system helps control where they are too. For instance, space elevators are tricky to have away from the equator, while most conventional rockets are so powerful and loud that we can't have them anywhere near a city, not even as close as airports on the outskirts tend to be. With that in mind, we'll be considering a lot of the launch systems discussed in our Upward Bound series and what their facilities might look like. Those will include conventional, reusable, and nuclear rockets, space elevators, space towers, mass drivers, launch loops, orbital rings, space planes, floating platforms on sea or in the air, and even more sci-fi scenarios like wormhole gateways such as we see in Stargate. Speaking of sci-fi, while we are principally focused on spaceports on Earth today, we also want to consider a more distant future and spaceports elsewhere, so we do want to look at putting them on other worlds, as for instance a cheap and dirty nuclear rocket is probably just fine on some airless radiation-blasted moon everyone lives 100 meters underground on. Speaking of other worlds though, we need to acknowledge that for us to have a need for big spaceports that folks and cargo move through in large quantities, there needs to be destinations for people to visit, and those will influence those spaceports too. If the majority of travel to space is to Earth orbit, as it will be for the near future and likely will be in a future where more space habitats are built in orbit of Earth than any other place, we're talking a very different sort of travel, hours, than traveling to distant worlds orbiting further from the sun or even around another sun. Alternatively, in some sci-fi wormhole gate case, your spaceports might entirely circumvent space from the equation and not need any special facilities far from the urban centers where they can be as loud as heck. That option is also available to space elevators, orbital rings, mass drivers, and space towers, as none of them have a big loud rocket engine going on, and some types of space planes which fly like normal planes till getting far from their launch location then turn on the big engines. For anything using a rocket, be it a chemical rocket or atomic, and this currently includes essentially all of our current and near-term launch vehicles, sound is a big issue. Fundamentally, sound is random excess energy vibrating into the local landscape and turning into pressure and heat, and it doesn't really matter if it's a big flaming jet or some hyper-accelerated ions. All that stuff coming out the back is hitting other stuff and making noise and heat. Only something very outside the loop like a neutrino rocket would get around that, and that's something we don't even have on the drawing board. If you didn't know, the decibel scale for measuring sound and how loud something is starts at 0 decibels, being the quietest audible sound a human can detect, or a perceived total silence. 10 times more powerful than that is 10 decibels. 10 times more powerful than that is 20 decibels. 10 times above that is 30 decibels. It is a very stupid unit of measure in that the original unit is the bell, B-E-L, named for Alexander Graham Bell, whose name has 2 L's. And in that scale, 2 bell is twice as loud as 1 bell and a tenth as loud as 3 bell, but a decibel, a tenth of a bell, conveniently makes the decibel system more confusing by using a logarithmic scale. Critical notion though is that something 100 decibels loud is a million times louder than something which is 40 decibels. 130 is a billion and 160 a trillion. The shuttle launch was 194 decibels, very nearly the loudest thing on Earth, which is not hyperbole. 194 decibels is the theoretical limit for undistorted sound in Earth's atmosphere, and it gets real debatable if it's a sound if louder than that. The Saturn V rocket did 204 decibels. At this sort of scale, sound is essentially shock waves of a blast. They aren't moving through the air, they are moving the air, and over 194 decibels you have an actual vacuum between pressurized shock waves. Krakatoa was so loud that it still measured 172 decibels 100 miles away. In general, sound falls off 6 decibels every time the distance doubles, so Krakatoa would have been 178 decibels at 50 miles and still 148 decibels at 1600 miles, which is well above the pain threshold of 140 decibels. This is a thing we want to be keeping in mind when talking about spaceports and picturing ones from sci-fi, because it's not the rocket being chemical that makes it loud, it's the sheer power of the engine interacting with everything around it. The shuttle launch was 12 billion watts, a billion times more powerful than your typical speaker. Even 3 miles away from the launch pad or 5 kilometers, the shuttle was still 120 decibels, which is also the volume of thunder from right near a lightning strike, and 1,000 times louder than your lawnmower or the headphones you're playing on max to hear over it, which are themselves 1,000 times louder than the typical conversational voice level. The ambient urban noise level is usually around 60 or 70 and as high as 80. If you're trying to avoid hearing the shuttle blast off from your local spaceport at above 90 decibels, it would need to be 32 times further away than what would make it 120 decibels or 160 kilometers or 100 miles. Bigger and more powerful engines, like to launch something like the USS Enterprise D, are even louder. Sound is critical deciding spaceports and why we spent this time discussing how it works, and it's not something you can fix without having engines running on different physics, like anti-gravity or magnets pushing right out the atmosphere, or something shooting weakly interacting particles like neutrinos or dark matter out the back. So how do we get around this? Well, if you want to have a spaceport near your city, it can't operate on those rockets and thrust approaches, and we'll get to those options. You can also do sound dampening, which we did at the shuttle launch site, but it's hard to dampen a rocket already in the air, and we're worried about the entire launch area, not just the pad, as that rocket hardly stops making noise just because it's a mile high, though a launch tower, well padded against vibration and empty of air in its launch tunnel, also works. This is essentially what a mass driver is. They probably would not be utterly quiet, but vastly quieter. The alternative is just to have your spaceports far from your cities. That's why when folks start talking about building artificial islands for launches or putting them in the middle of nowhere, it makes sense, even when it effectively requires building decent-sized towns just to operate the things. On the other hand, when we talk about seasteading, the notion of building artificial islands that are micronations in their own right, folks talk about making a rocket launch site and using that as a Kickstarter for some combination of port, resort, casino, and independent nation state, and I'm not sure a rocket launch so loud it shattered every glass in the island would make for a good place to visit. This works much better for alternate launch forms like the space elevator, which is much easier to build at the equator of a planet, and which means you either need an artificial island as its base or some deal with one of the few countries on the equator. That equatorial advantage applies to more than the space elevator too, but to virtually every launch option. It takes a certain velocity to orbit Earth, and since Earth spins, launch with that spin gives you a small free boost of speed, and that's biggest at the equator where the world spins 460 meters per second versus, say, New York City at about 350 meters per second, or the North Pole at 0. Equatorial spaceports then have the advantage of cheaper launch costs, mostly, and better weather, mostly. Indeed, the ideal site for a mass driver, a big cannon we can shoot craft down to get into space, is running at the side of a tall mountain on the equator, making Mount Chimborazo in Ecuador, at 6.3 kilometers tall, the furthest point from the Earth's center, and the one moving fastest too. And the thinner air doesn't hurt either. Mount Chimborazo probably holds the status of most ideal site for a spaceport. Equatorial mountains on other worlds likely will be early settlement sites for the same reason. Now, speaking of mass drivers, this is a system that can be placed in a city because the ship is not being rocket propelled and is not moving through air. The general notion is to have a long vacuum tube ramp that the ship is propelled down magnetically till it exits at a very high speed and altitude and low air pressure. You could have this begin inside a city as a result, indeed underground like a subway if you want, but will exit thousands of miles away, and there's lots of right-of-way issues through a lot of valuable real estate, including building a pipe as wide as your ship hanging over the landscape for that whole distance. I could imagine many cities in a region using a single long mass driver that had multiple connecting tubes that curved and joined together before the ship was going too fast for such maneuvers, which certainly saves on cost given how much time a ship spends in a given piece of the tube. It would also be nice to have multiple ships able to move through the mass driver at once. You would also tend to put this out on the sea anyway, coming from coastal ports, not because it needs to, but because it cuts down the right-of-way issues for building it, a feature the mass driver sibling, the launch loop, has, that we'll get to in a minute. Now, I mentioned only one ship going through a mass driver as a cost issue. Ideally, you want many going through at once, and we have the parallel concern with space elevators. Space elevators are often seen as the ideal form of ground-to-space travel, because once one is built, it takes very little energy to go into orbit by climbing it, but they're not quite the wonder method often implied, even ignoring that they require material strengths we haven't got yet. Now, technically, they do not have to be on the equator. There's a trick around that which essentially involves placing a single station up at geostationary orbit, then having 3 or more elevators coming down from it like guy wires, so their forces balance out. And this allows you to use one station in space for multiple ground-side spaceports, as well as letting you put those spaceports anywhere so long as the forces balance out to keep it at the equator, so at least one on each side of the equator. This also presumably lets cities team up to operate and maintain one, and represents another often neglected use of the spaceports, which is rapid transit off the planet and right back on it again. One might imagine a pyramid of several space elevator tethers ascending to that geostationary space hub, but with secondary stations partway up and secondary tethers running right to the neighboring lines, allowing you to get out of the atmosphere, then pour on the juice to another tether and drop to another spaceport, shaving hours off the trips made at subsonic air travel speeds. This of course requires even stronger materials than a normal single-line equatorial elevator does, but if you can do it, you probably would, because the thing folks tend to miss about space elevators is how long they are, comparable to the circumference of the planet at the equator, not the couple hundred kilometers it is to low orbit. And while you could climb up one part way, then drop and coast in on wings like a plane to a location, after building lots of speed on the drop, you would have to drop because you're not at orbital speed on a space elevator until you get all the way to geostationary orbit 36,000 kilometers up. Orbital speeds of Earth drops the further away from Earth you go, and your own speed from spinning with the Earth rises as you go up, which is why Mount Chimborazo is also the fastest moving place on Earth. On a space elevator, your rotational speed around Earth's center rises as you rise, while the necessary orbital speed drops, until they match up way out at geostationary at a mere 3 km per second, not the 8 km per second it normally is to low orbit. When you're 400 kilometers up, which is how high the International Space Station is, and you've gotten there by climbing up a space elevator or space tower, you're only going 492 meters per second, just 32 meters per second or 72 miles per hour faster than the speed of the equator surface below. Not really a big speed bump, though it would rise as you got higher. It would also rise as you dropped though, in terms of vertical speed, not lateral speed, but that's a long drop through a lot of very thin air that lets you use any wings you might extend to convert that speed into a direction of your choosing. That would seem to indicate these would be great ports for getting around Earth too, but they have a bottleneck. That space elevator is holding itself up, all 36,000 kilometers and more, and every pod traveling up it at any moment, which also gains speed to climb by shoving down on the elevator, straining it further. and they exert the most force and braking force on that tether down low, where the most tether is hanging and where gravity is strongest. So pragmatically, unless you've got a very cheap material that's quite strong even compared to graphene that lets you do tons of pods on a space elevator tether at once and place them at angles off the equator, space elevators do not make for ideal spaceports from cities, though are handy for being quiet. I could imagine cities sprouting dozens of these tether cables though, and have airports just outside the city that personal winged aerospace ships could fly through to get to the airport, climb the tether, then drop and glide to another spot, though I suspect this would simply save fuel, not time in most cases. Space towers are the alternate way of building tall, and they have the advantage that you only build as high as you need. The problem is, like all active support, you need to keep the power running, and you really benefit from having cheap energy and/or superconductors and/or materials that shield well against magnetics. Now, for a discussion of how active support works, see either our launch loops, space towers, or orbital rings episode, but in summary form, you're keeping something from falling by constantly pushing on it. This is easiest done with tiny streams of objects subject to magnetic attraction or repulsion, but doesn't require electricity in and of itself. A piece of paper hanging over an air vent is actively supported, so is an object orbiting Earth. For safety, we also have batteries, which superconductors are amazing for too, for uninterruptible power supplies, and also parachutes for slowing large objects that might be hanging in the sky and suddenly begin falling. So things like launch loops, orbital rings, and space elevators are not nearly as dangerous as they sound. They also don't drop at re-entry speeds, they just fall down like any other object, and a space elevator, if cut, just flies off into space above the cut, and the segment below the cut just plops down from above. And given that space elevators rely on super strong materials to operate, well, those also make for ridiculously light parachutes. Now, when it comes to sea study and small nation states that act as spaceports, active support makes this a bit better as an option, and the launch loop is a great example of an active support system that does best at sea. Conceptually, imagine you were to shoot a big cannon and its shells moved so fast and high it landed a couple thousand kilometers away, then upping that to machine guns, sending a constant stream of them, then keeping a big magnet hanging over the stream of iron slugs. Instead, we do this with a big tube and a stream of magnetic materials being pushed by electromagnets, but it results in an aborted orbital path that you can use as a big launch platform, turning electricity directly into spaceship velocity, letting you plug it into a big nuclear power plant or whatever on the ground, or floating in the sea and running it. You can also lower and drop it to avoid weather issues. A space elevator getting hit by a hurricane is problematic, for instance. Not nearly as bad though as the notion of a super long cord of super strong material whipping around in a hurricane probably sounds, but one advantage of a Lostrum loop is that if you cut the power it slowly descends, and you can speed that descent up by tapping it for power. Indeed, most of our active support systems make for very good energy storage systems in that sense too, much like a flywheel but without the friction losses. A space elevator can actually be detached and reeled up above the atmosphere if needed, though reconnecting it might be quite a pain. Similarly, the orbital ring, which makes use of tethers too, can just pull any threatened by the weather, though it's also a lot sturdier against that. We'll come back to those though. Now, I suspect we'll have our first commercial spaceports before we have orbital rings, and those early ones will probably be a mixture of airport and launch pad, one to each side as it were, decently far from any city or existing built-up area, and close to an eastern coast so the launch is over the ocean. Expect the facility itself to just be very buffered against sound and vibration, and possibly have any hotels and hospitality along a tram line running perpendicular to the direction of launch, so north or south of the facility and launch pad. Deserts work for this too, incidentally, and for something like a mass drive or a launch loop offer the option of solar power, as would floating solar panels on the water in the ocean or in the air. So also potentially on a big helium balloon a kilometer across that your launch vehicle can basically fly out the side of and ignite its rockets as it heads off. See our Sky Platforms or Cloud Cities episodes for more discussion of that approach. I would expect that to be the rough setup, whether it's on land or sea, coast or desert or mountains, for any spaceport built, if and until we have another big shift in the space launch method away from rocketry. That combination of airport and spaceport, located in the middle of nowhere, with the spaceport on the east side of things and everything highly insulated against sound and connected to the north or south. Spaceplanes though might get around a lot of these issues, but as we noted in that episode, it's very hard for us to make an air-breathing vehicle get to orbital velocities if it has to carry its own fuel. So the approach of having a personal vehicle you could fly from your airport, or even your home garage, right into space, relies on either a compact high power-to-weight ratio nuclear drive, fission or fusion, or power beaming, which as we know in our Spaceplanes episode is actually very simple. You just build a pair of scramjet stovepipes, which are particularly microwave receptive, and then let them take the place of the normal reckless fuel burn of scramjets. A scramjet itself, or stovepipe, is a mostly non-mechanical device whose purpose is to let you suck in air and superheat it, and shove it right out the back. Its geometry is doing all the heavy lifting so long as you supply heat. In such a setup, your spaceport is just an airport and your spaceship is similar to a personal or commercial airliner modified to receive microwave energy beaming. If the beam is lost, the vessel just glides till it's reacquired, and unauthorized vessels can just have their beam shut off. In that episode I referred to it as probably the only plausible pathway under known science for people to own their own personal spaceship they could fly to orbit in, partially because big improvements to nuclear options still means someone personally owning and piloting something nuclear, whereas beam-powered ships with small batteries or a small conventional engine for backup or takeoff avoids your neighbor having a super powerful device in their garage they could kamikaze into a city at Mach 10. That is another reason you probably want your spaceports far from urban centers, accidents, and malice, and even small spaceships carry all the destructive potential of a train wreck or even a small nuke in a tiny package. I haven't mentioned it as much, but spaceships have to land too, not just take off, and they have to pass overhead at hypersonic speeds, so it pays to be keeping crash scenarios in mind and what to do if someone does decide to do a suicide run, or crash one by remote control. The good news about landing ships is that it can be done at conventional landing strips. They just aerobrake and head on in like a plane at that point, or come down as a reusable booster rocket does. Now this is one advantage of space towers, they get around the whole atmospheric drag thing that costs a lot of fuel on launch, and while trying to land on one is a bit trickier than aerobraking, you might do that to recover energy rather than burn it all off in the atmosphere. Indeed, a developed spacefaring world might have bans on aerobraking outside of emergencies to keep the heat down and to minimize sky noise, and the distraction of giant fireballs constantly raining on the planet as thousands of giant ships take off and land in a given day or minute. A spaceport on a space tower might be a big pad high above the planet, or it might be a full launch tube extending kilometers below ground and hundreds or even thousands of kilometers above ground. You don't necessarily have to follow straight lines either. A spaceship can only turn so fast without pancaking its crew, but the tiny electrically charged particles or metal beads or whatever that you use for the active sport's working fluid can turn at pretty high Gs, permitting you to do a pair of towers leading to a long flat runway between them, hanging right over the atmosphere. The ships using that still need to accelerate, but they can leach energy off the active support structures for speeding ships up though, avoiding carrying lots of fuel or needing a giant loud and bright rocket flame out the back. Big thing to remember for both space towers and orbital rings though is that when you get above the atmosphere on one, you are not in orbit. Step off the side of a space tower roof or orbital ring and you will fall down to the ground. And I assume people will do this constantly given that a pressurized skin suit and wings, or a parachute, will let you glide down safely for the sport of space diving, the ultra-high-octane version of skydiving and cliff jumping. Fundamentally, a space tower really is just a very tall building, though I'd imagine a very tall cell phone tower might be a better analogy, even if it might be a tube kept vacuum tight to serve as a launch tube. You could also have many along the path of a mass driver to allow one to exit well above the atmosphere and operate with much thicker components and bigger payloads than the kind we tend to contemplate now, using balloons or similar as part of the ramp's support structure. Now in the long term, the orbital ring would probably come to dominate space launches, and essentially eliminates ground-side spaceports to be replaced with something like a local train terminal. One problem with space elevators is they need to have a super strong material that you can make a 40,000 kilometer long cord out of, able to hold up its own weight plus others, and we do have some that can barely do this on paper, using taper designs and Earth's lowering gravity as you get farther away. See the Space Elevators episode for discussion of that. However, those same materials do just fine for a tether only 100 kilometers or so long, and that same active support method works much easier for an orbital ring, which is fundamentally just two hoops around the planet, one inside the other, one spinning faster than orbital speed, and one spinning just as fast as the planet below, whose combined momentum equals what's needed for a regular orbit. This gives you an apparently stationary ring hanging in the sky, to which you can drop tethers or even just fly up to with a plane modified for high altitude, though a ring could be way above the atmosphere or even hanging just above mountain heights, though it's not too handy for launching spaceships that deep in the atmosphere. What's more, while orbital rings not above the equator will precess and wobble left to themselves, those same super strong tethers can counteract that and pin it to a path circling Earth, not along the equator, cocked at an angle, and you can also connect up to it with space towers which can serve as additional support or backup, and you can then run electricity up those or the tethers. Though you might let it roll instead and leave your tether hanging like skyhooks for planes to link up to on whatever schedule brought the precessing ring near the service area. In such a case, any sort of cable even vaguely in the space elevator strength region ought to be able to hang a small spaceport at the end of that, with parachutes built in just in case of catastrophic failures, for planes to link up to, which I suspect would make for some very popular resorts or mansions too. Now, classically, we assume the shortest possible tether to require the least strength, which would be straight down, but if you're trying to stabilize one from precessing, you want those tethers out at an angle like a guy wire, which also means you could run a cable car up one carrying people and cargo back and forth, and given that one that runs out wide at a 60-degree angle from one 400 kilometers up would represent an 800 kilometer long tether stretching sideways 700 kilometers to either side of our orbital ring, makes for a very large surface area, especially given that none of the tethers need to be as long as each other or at the same angle. Meaning some orbital ring of that type could have a big long wire reaching up from atop a tall building in a city to the orbital ring from any city within a 1400 kilometer wide band. That's a pretty big surface area, and if you have multiple rings around a planet at different angles and slightly different altitudes, you could drop a tether between any two of them at any of the 2 points of overlap. This both eliminates ground-side spaceports and vastly increases their number too, because they go from a handful of big ones far from habitation to thousands of them stretching out from every city to every orbital ring they can run a tether to, like a train station or an exit ramp truck stop. There's no big noise or disruption going on here either. They're just a cable car moving at whatever speed we feel like, probably speeding up to a few hundred kilometers an hour to out of the atmosphere, and maybe not speeding up much more than either, up to space from any city that can afford one in an hour or less for an energy cost comparable to driving your car to the neighboring town. If you felt like making very big rings and very robust tethers, you might see those become train station equivalents of spaceports, with huge strings of cars running that tether like trains on its rails. You can, hypothetically, even scale something like that up to mean a physical highway cars could drive on, to space, though they need a pressurized tunnel or to be modified for vacuum presumably. It's always hard to guess how space development will take place, but I tend to think this is the best candidate for how the situation will look on Earth in a couple centuries as we develop orbital space, get millions working and living there, and head out to colonize our moons, our planets, and the moons around other planets, and all those asteroids, and probably how it would remain for an extended period unless we did get some technology like gate-style wormholes, which might circumvent space travel entirely. Now, if you've seen Stargate, you know the wormhole type in question, and kudos to Peter Hamilton for being the first author I know who considered the idea that you pretty much leave these on all the time and not have folks walk through them or fly through them in favor of running trains, electric cables, and fiber optic data cables through them to the other world. These, if we could ever make them, would probably replace all spaceports and arguably aren't spaceports since they circumvented it entirely. One other farther tech option is spaceports by teleportation. You just beam yourself to space stations, and for a digital civilization of AI or folks living as uploaded minds, this sort of teleportation is vastly easier. Your spaceport becomes a radio dish. Though even then, high bandwidth cables running up to orbital rings probably works better. Atmospheres aren't any kinder to signals than to spaceships trying to plow through them. But those aren't the norm in the universe, let alone our solar system, and to close out for the day, let's quickly contemplate spaceports on other worlds. Now we've got two big factors here. First, Any spaceport we build off Earth is our keystone to settling that world, the entry port, not the exit, so you want one you can quickly assemble and easily to, and initially landing is more important than taking off. Second, each world has different conditions making landing or leaving by different methods preferred. On any airless world like the Moon, your mass driver is your paydirt because there's no need to elevate one above the atmosphere. You can just run a track of magnets right along the ground until the ship speeds up enough to leave it, and usually not need to speed up too much since airless worlds tend to have low gravity. Landing is a whole different story. You need fuel for that because you can't aerobrake, and trying to connect to some landing strip to slow you down at thousands of meters per second sounds like a recipe for disaster, maybe even with computer pilots reacting in nanoseconds. Here you might prefer a space elevator, which are much easier to build around fast-turning and low-gravity worlds, that you could have whirling around your planetoid for a ship, moving at about the same tangential speed, to connect up with them then slowly be winched down on, like big tentacles extending out to form an asteroid to catch spaceships and eat them. Spaceport Kraken. Works just fine for taking off too, and offers a longer takeoff track to speed up on, as smaller moons and asteroids don't offer a lot of diameter or circumference for a track. Getting off those requires virtually no fuel, but speeding up more would. And so if you want to leave at a good speed without blowing tons of propellant from some world with a tiny escape velocity, tentacle-like space elevators and tethers might be very handy. Indeed, I could imagine a number of circular rails wrapping such a planetoid with long tethers swinging around them just to allow you to have your tentacles extending and spinning at directions the spin of the object would not permit. This works on orbital rings around planets too, but strikes me as one of those things like skyhooks that represent dangerous clutter if you have a lot of traffic. Alternatively, space is huge and asteroids small, so the asteroid Kraken spaceport does not have those clutter issues. Places like Venus easily allow aerobraking, ditto Titan. Any fast ship heading to the moon of a gas giant can slow to a better orbital speed by skimming that gas giant's atmosphere before winging out to whichever moon they were destined for. On such worlds though, your spaceports might be floating sky platforms, hanging over Venus or Jupiter by buoyancy, mining the clouds for gases, volatiles, or fusion fuels. And for the latter might skip buoyancy for electric engines or fusion candles. There's a virtually unlimited number of possible options for which types and variants of spaceports and launch systems we might use on other worlds for us to imagine and discuss and hopefully one day build. I would make a joke about the sky being the limit on spaceport options, but it obviously is not. Whenever we find ourselves discussing space launch methods and megastructural concepts like orbital rings and active support techniques, there's often an urge to go into the math a bit deeper, and I avoid doing that because our episodes are meant to be accessible to everyone. At the same time though, I really can't encourage everyone enough to look into a deeper mathematical and scientific level on a lot of these concepts, because it does open up a whole new level of understanding and wonder. Math and science can be pretty intimidating, but with the right learning path they will unfold to be clear, intuitive, and horizon broadening. The key is to find that right learning path, and our friends over at Brilliant have, by embracing interactivity and feedback for hands-on and intuitive learning. Brilliant has always focused on interactivity, but earlier this year, Brilliant upped their interactivity on their platform to a whole new level, like with their newly updated Geometry Fundamentals course, and they continue adding in more and more interactivity to all their courses. It is never too late to start learning something new, and Brilliant is a great place to start. Brilliant is an interactive STEM learning platform that helps you learn concepts by visualizing them and interacting with them, which is, hands down, the best way to learn. On Brilliant, it is not about memorizing or regurgitating facts for a test. You can pick a course you're interested in and get started, be it the basics or advanced. If you get stuck or make a mistake, you can read the explanations to find out more and learn at your own pace. Knowing and understanding math, science, and computer science unlocks whole new worlds, and if you'd like to start your journey to them, you can try out Brilliant for free and get 20% off a year of STEM learning. Click the link in the description down below or visit brilliant.org/IsaacArthur. So we're looking at how to get from ground to space today, and next week we'll look past getting into space to the colonization strategies we might employ for settling the solar system. Then we'll have our mid-month Sci-Fi Sunday episode to take a look at one potential method of getting out of our solar system by fording space to travel instantly to new stars. Then in 2 weeks we'll return to our Alien Civilization series to contemplate aliens with tempers and aggressive tendencies in Belligerent Aliens. Now if you want to make sure you get notified when those episodes come out, make sure to subscribe to the channel. And if you enjoyed the episode, don't forget to hit the like button and share it with others. If you'd like to help support future episodes, you can donate to us on Patreon, or our website, isaacarthur.net, and Patreon and our website are linked in the episode description below, along with all of our various social media forums where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. Until next time, thanks for watching, and have a great week.